This finally connects up these abstract Hilbert spaces with things you can go out and measure. Okay, so axiom 3. Now we're going to connect things up with the real world somehow. Every so-called observable, it's the term that we use, every observable, everything you might want to ask. And observables could be things like position, momentum, energy, angular momentum. There's a whole list of things it could be. Every observable corresponds to a self-adjoint. This can be generalized, by the way, to positive operator value measures we're going to talk about. It can be associated to a self-adjoint operator or matrix. Think of it again as an n by n. So the density matrix is an n by n matrix. A. Self-adjoint means that the thing is equal to its adjoint. If you imagine transpose and complex conjugate, doesn't change it. This is a very special feature. It means this thing has a complete set of eigenvectors and eigenvalues. You may not remember what eigenvalues are, but we'll talk a little bit about that. To this thing, there is associated a list or so-called spectrum. The terms eigenvalue, eigenvector, and spectrum were introduced by David Hilbert, whose name is attached to these Hilbert spaces. David Hilbert, of what are called eigenvalues. And these are real numbers. It's a list of real numbers. I'll call these numbers lambda 1, lambda 2, ... There are at most n of these. At least at most n distinct ones of these. Given that we're in a Hilbert space of dimension n. If you have an observable with more than n, you need a bigger Hilbert space for it. These numbers are associated with this thing in what sense? In the sense that for some vector, I'll call that vector lambda sub a, when your operator acts on that vector by matrix multiplication, what comes out is the number itself times that vector. Actually, I usually draw these vectors without lambdas. I start with this. Label the vectors by the label A. What comes out is that number out front. When a matrix multiplies a column vector, you can get any. Just totally scrambles it up. But if A is an eigenvector, it's a very special kind of vector. When the operator acts on it, you don't get just anything. You get the vector back again, the same exact vector with a number out front. And that number out front is called an eigenvalue. And a self-adjoint operator has this unique, distinct list of eigenvalues that come out. I can give you an equation that tells you how they're uniquely determined by it. This list of numbers are called the eigenvalues. And what does axiom 3 say? It says the possible results of an observer measuring the observable represented by A are its eigenvalues. So if you wondered, if you took a linear algebra class, what about eigenvalues, and they're just sort of like floating around the back of your head, when am I ever going to need these? They're rather important. A self-adjoint operator has a full list of these, and to say that we're representing an observable by one of these is to say that if you go out and measure energy or whatever it is you're measuring, what you can get numerically in your measurement is one of these numbers and only these numbers. These are the numbers you can get. When people talk about what are the energy levels of the hydrogen atom, you measure the energy, that's represented by a self-adjoint operator, turns out to be the Hamiltonian, as it turns out. And the possible energy levels for the hydrogen atom, it's various negative 13.6 electron volts times 1 over n squared, when n is the principal quantum number. That list of numbers, those are the eigenvalues of the Hamiltonian. At least most of them. Well, the discrete ones. There's also continuous ones, scattering, but whatever. So this finally connects up these abstract Hilbert spaces with things you can go out and measure. Notice I haven't said anything about the quantum state yet. This is a statement about the possibilities of measuring a given observable. They correspond to the eigenvalue spectrum of a particular operator.